Welcome back to Learning as a Hobby. In this video, I'm going to be going over section 1.2, my notes for section 1.2 in Theodore Shifrin's Multivariable Mathematics textbook. And that section is on the dot product. So I'll go through, like I usually do, I'll go through the notes. I'll do any proofs or examples that he has. I don't think he has any examples here, but there are a few proofs and some definitions. So I'll go through the notes and I'll prove the theorems that he has. And then in the next video in the series, I'll do the recommended exercises for this section along with some other ones. So let me bring up my notes that I took down. Okay, so like I said, section 1.2, it's on something called the dot product, and he recommends to do exercise 9, 14, 17, and 20 in the section, but there's a lot of problem exercises at the end of the section. Some of them look pretty interesting, so I might try to do a few more than just the recommended exercises in the exercise video, but we'll see how that, we'll see how that goes. So let's start on the definition of the dot product. Right, so this is the definition given x and y in R2. He starts with the definition in R2. This should be a dot here, not a minus. You can define the dot product in R2 where x has components x1, x2, y has components y1, y2. This is the way that you find the dot product. You take component by component, you multiply them together, and then you add them up. So x1, y1 plus x2, y2. Okay, and more generally, if you want to define it for vectors in Rn, so in this example, sorry, in this part of the definition, if x and y are vectors in Rn, meaning they have n components, so x has components x1 up to xn, and y has components from y1 up to yn, then it's defined, the dot product is defined in a similar way. You just multiply each of the respective components to each other, and you add the products up. Okay, so x1 plus y1, sorry, x1 times y1 plus x2 times y2, dot, 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 all the way up to xn times yn. So that's the definition of the dot product. Okay, and there's a bunch of properties that dot product has, which he lists in proposition 2.1, and we'll prove these. I'll read them out first, and then we'll prove them. Property 1 says x dot y is equal to y dot x, meaning that the dot product is a commutative operation, right? That holds for any vectors in Rn. If you take the dot product of a vector with itself, it gives you the length squared, right? Which means that the dot product of a vector with itself is always non-negative, and it's only 0 when the vector x itself is the 0 vector. Property 3 says if you take the dot product of a scalar multiple of x with a vector y, that's the same thing as taking the dot product of x and y and then scalar multiplying. Actually, it's not scalar multiplying here. This would be just product of real numbers, but this would be a product of real numbers, but this would be a scalar multiple. That's because the dot product gives you a scalar when you multiply it out instead of a vector. Okay, property number 4 says there's a distributive law, so x dot y plus z. If you add y plus z together and then take the dot product of that vector with x, the dot product distributes. So x, that's the same thing as x dot y plus x dot z. So let's actually, before we get to any other theorems, let's actually prove each of these. I'll have to do it on the whiteboard. So let me bring up the whiteboard. And I may have to go back and forth just so in case I forget what the theorems are. So property 1 was a commutative law, I think. So x dot y we want to show is equal to y dot x. Okay, so in other words, so proof, this holds for any x, y, and Rn. So let x, y be vectors in Rn. Then x has components x1 up to xn. Y has components y1 up to yn. And if we consider x dot y, whoops, the dot product is defined to be x1, y1, plus all the way up to xn, yn. But each of those are products of real numbers, and we know that real number multiplication is commutative, so you can rearrange the products here. And that's the same thing as y dot x. Right, so that shows the first property holds. The second property, I forget what it was already, so let me go back and check. X dot x is the length of x squared. Let's actually do that. IF, F, if you're not familiar, this stands for if and only if. All right, so proof let x be a vector in Rn. Take x dot x. This is x1 dot x1 all the way up to xn dot xn, which is x1 squared all the way up to xn squared. And if you remember the definition of the length of a vector, we went over that in the last set of lecture notes, or the last set of chapter notes. This is the square of the length of the vector by the definition. So this is length of x squared. And since this is a real number, squares of real numbers are always non-negative. Okay, and for the last part, if x dot x is equal to 0, then that means x1 squared plus xn squared is 0. So the only way that a sum of squares can be 0 is if none of the terms in the sum are 0. So this implies x1 equals x2 equals dot 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 xn equals 0. And if we go backwards, if x equals the 0 vector, that implies x dot x is 0 times 0 all the way up to 0 times 0, which is 0 summed to itself n times, which is just 0. Okay, so that proves that part. Part 3 was the kind of associative law for dot products. Right, for any x, y in Rn, and c in R. Right, so proof cx dot y is equal to cx1 times y1 plus cx2 times y2 plus dot 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 up to cxn yn. And these are products of real numbers, so we can use the associative law. And by definition, that's c times x dot y. Okay, and I think the last property was the distributive law. Okay, so proof, let x, y, and z be vectors in Rn, then y plus z, sorry, x dot y plus z is x dotted with the vector y1 plus z1 up to y2 plus z2, which is equal to x1 times y1 plus z1, and so on. And these are, again, real numbers, and there's a distributive law for products of real numbers. Sorry, for distributing products over sums of real numbers. And there's also a commutative law, so I can rearrange this sum of products. And the first sum in the parentheses is x dot y. The second one is x dot z. Right, so that proves the four properties that he has listed for the dot product. Let me go back to the notes. Right, there's a corollary to that, which says that the length of x plus y squared is equal to the length of x squared plus 2x dot y plus the length of y squared. So this follows, he calls it a corollary because it follows directly from those properties. So let's actually prove that one next, and then I'll explain the definition that's right after it. Right, so this is corollary. Oops, plus that plus y squared, length of y squared. So this follows, like I said, directly from those properties. So consider x plus, sorry, consider the length of x plus y squared. This is x plus y dot x plus y by property 2, I think it was, right? This is, and then there's a distributive law, so this is x dot x plus x dot y plus y dot x plus y dot y. Okay, x dot x is x, the length of x squared, and x dot y is the same thing as y dot x by the commutative law, so that's plus 2x dot y, and y dot y is the length of y squared. Right, so that's the proof of the corollary. Like I said, it just follows directly from those properties. There's a definition that he has next. So while I have the whiteboard in front of me, maybe I'll just explain that first. So here, if you have two vectors that are perpendicular, let's say, if you remember, perpendicular means they meet at right angles. So let's say this is the vector y, and let's say this is the vector x. So they meet at a right angle here. If we look at the length here by the Pythagorean theorem, the length of this triangle should be what should I call it? This should be actually, let me do it the other way so I can use the sum. Let me make the parallelogram here. So we have this rectangle, and let me use this one so I can use the sum of the two vectors. The diagonal here, is, if you remember, is x plus y. Right, then by Pythagoras, the length of x plus y squared, which is the hypotenuse of this right triangle here, should be the length of x squared plus the length of y squared. Right, and if we set that equal to what we just found by this corollary, that should also be equal to the length of x squared plus 2x dot y plus the length of y squared. And if we subtract the sum of x squared, sorry, if we subtract the sum of the length of x squared plus the length of x squared from both y squared from both sides, notice that these cancel, and we get that 2x dot y is equal to 0, or we can divide by 2, and that gives us that the dot product of x and y is 0. Okay, so if the two vectors are perpendicular, meaning that they meet at right angles, in other words, the angle between them is a right angle, 90 degrees, right? Then the dot product is 0. Furthermore, if at least one of the vectors is 0, so also if at least one of x or y is the 0 vector, then x dot y is 0 as well, because the components of one of them is always 0. So when you take the product of any number with 0, you get 0, and so on. So the fact that the dot product is 0 when the angle between the two vectors is perpendicular, is a right angle, or if one of the vectors is a 0 vector, then the dot product is 0. We get the next definition that we have in the notes. Let me go back there. We say that the two vectors are orthogonal in those cases if the dot product is 0. Right, so we say the vectors x and y are orthogonal if the dot product between them is 0. They use orthogonal instead of perpendicular because of that one case where one of them can be the 0 vector. Right, so in that case, I guess we consider the 0 vector to be perpendicular to every other vector, or orthogonal. So, right. So orthogonality is actually very important in linear algebra and coordinate systems. So we want to know how to decompose a vector into a sum of vectors, one of which is parallel to some other vector, plus a vector that's perpendicular or orthogonal to the other vector. So looking at the picture that I have here, if the vector here is x, so this vector here is x, then the red vector is the vector component of x in the direction of the vector y, and the blue vector, this is called x perp for perpendicular. This one is x perp. That vector is orthogonal to the red vector, so meaning that they're perpendicular. Right, so we can write the vector x in terms of those two vectors, the red vector and the blue vector. So in other words, if x is the parallel vector plus the perpendicular vector, the parallel vector to y, just using the definition of parallel vectors, means that the parallel vector, x with the parallel symbol in the superscript, is some constant or some scalar times the vector y. And if you take the dot product of y with x, where x is written like this, then we get y dot x parallel plus y dot x perp. Y dot x perp is 0 from the definition of orthogonal vectors, and since the parallel vector x is c times y, then you get c is equal to x dot y over the length of y squared, and this formula is called a scalar projection of x onto y, or actually without the square, that would be the scalar projection. But this formula gives you the value for C. And then to get the perpendicular vector, you take the difference of x with the projected vector of x onto y. Right? And you can prove that this is perpendicular by taking the dot product, which maybe I can fit in on the side over here. So if you take y dot x perp, this is y dotted with x minus x dot y over length y squared times y. This is y dot x minus x dot y over length of y squared. And then you get the y dotted with y, which gives you length of y squared. Notice these cancel, so you get y dot x minus x dot y, which is 0. Right, so that vector is perpendicular to y. And then just some terminology. This vector is called a vector projection of x onto y. Sometimes people write it, instead of using this notation, you'll see people write it like this. So this stands for the vector projection of x onto y. Okay, next definition, let xy be non-zero vectors in Rn. Then we define the angle between x and y to be the unique angle theta, satisfying, so theta has to be between 0 and pi, so between 0 and 180 degrees, such that cosine theta is x dot y over the length of x times the length of y. Let me just show you where that formula comes from. This is a really important formula for giving the geometric meaning of the dot product. So did I share my screen? Okay, so let's say we have the vector x and the vector y, and this is the angle theta. Right, so if we take this right triangle, then the blue vector, let me draw it in blue. No, let me draw it in red actually, because I did that in the other picture. So this is the red vector here is the vector projection of x onto y, or in other words, this is c times y over length of y. Or actually, the way that we define c actually it includes the length of y. So that means that cosine of the angle theta is equal to, if you remember from trigonometry, this is the signed length of x parallel divided by the length of the hypotenuse, which in this case is x. Right, so that gives you the signed length of x parallel is the actual value of c, whatever its sign is, it has the same sign, times the length of y. And the length of x is given by this symbol here. And we know what c is. We've just found the formula for that. That's equal to x dot y over length of y squared. And here we're multiplying by length of y and dividing by length of x. And notice that one of these cancels. So this is x dot y over length of y times length of x. Right, so that's where the formula comes from. Usually people don't write it in this form, but people usually write it in terms of the dot product. So x dot y equals length x, length y times the cosine of the angle between them. But they mean the same thing, as long as x and y, the length of x or y is not 0. So That's where that formula comes from. The next important thing in the chapter is the Cauchy-Schwarz inequality, which we've actually seen before in a different context in Spivak's book. We actually proved this, the Schwarz, he called it the Schwarz inequality in his book. So here we have Cauchy-Schwarz, which I think I mentioned that I think the Cauchy-Schwarz is a generalization of the Schwarz theorem when you're dealing with more dimensions than just two or something. So if x and y are in Rn, then the absolute value of x dot y is always less than or equal to the length of x times the length of y. And moreover, equality holds if and only if one of the vectors is a scalar multiple of the other. So let's prove this theorem. All right, Cauchy-Schwarz says this is true, so proof. Here you take, so consider this sum squared, so t is some scalar. The proof here, if you'll notice, if you watched the videos on that I did from Spivak's book, you should probably recognize the proof here. It's virtually the same proof. So this is equal to, from our definition of the length, this is equal to the length of x squared plus 2t x dot y plus the length of y squared t squared. So notice you end up with a quadratic function in the quadratic function in the variable t. So note this is a quadratic function in t. So we can figure out what the minimum value would be, which would be at the vertex. So the min value, I know it's a minimum because this is positive, right? The leading coefficient is positive. The minimum value is at the vertex, or happens at the vertex rather. So min value is when t equals what's the vertex here? Negative. It's if you remember the formula, negative b over 2a, right? B in this case is so negative 2x dot y over 2a squared. A is the length of y squared. The 2's cancel. Okay, and the minimum value we can find by plugging this value for, maybe I should give this an actual name. Let me call it t0. We can actually plug that value for, into the polynomial here to figure out what the smallest value is. So in other words, t0 squared times length of y squared plus 2t0 x dot y plus length x squared. Right, this is, let's see, if we square this, we get x dot y squared over length y squared plus x dot y squared. We have a 2 in front. X dot y. This becomes a minus over over length of y squared. Okay, plus x squared. And this gives you length of x squared minus x dot y squared over length y squared. Okay, and we know that this is always positive because, let me write it over here. So actually, I don't want this to be too confusing. This is always greater than or equal to 0. Because it's a square of real numbers, right? It's always non-negative. So this is greater than or equal to 0. And if you solve that for x dot y, you get x dot y squared less than or equal to length of x squared length of y squared. Take the square root of both sides and you get absolute value x dot y less than or equal to length x times length y. Okay, and if and only if equality holds if and only if when one is a scalar multiple of the other. That happens because x plus t y equals 0 when x is equal to negative t y, or so in other words, one is a scalar multiple of the other, or if t is 0, then one of them would be 0. So that's when equality holds. Let me go back to the notes. I think there's one more thing to prove, which is the triangle inequality. Again, you should recognize this from Spivak. So the triangle inequality we can prove just from the theorems that we already have. So let me just finish up with that. All right, proof this holds for all. All right, so if we take x plus y length squared, this is this. We had a corollary that said that, and by Cauchy-Schwarz, this is less than this is the absolute value. That's right, the length of x plus length of y squared, and then you just take the square root of both sides, and that gives you the triangle inequality. Okay, that's the end of the notes for section 1.2. So the next video in let me just stop the screen share. So the next video in this series will be the exercises for section 1.2. I'll see you guys in the next video.